water and launched at high pressure. A water rocket is lightweight and designed to fly short distances. Our dream is to get the rocket to fly the furthest just by using water and air pressure. A water rocket is not just a thought, there are many scientific principles behind it. Our experiment is basically taking these 4 bottles and seeing which one can fly the furthest. The bottles are designed like this. The rockets will have their launch angle, their launch angle and their water-to-air ratio change, such that we can test all the possible configurations. Example, the rocket at the top left will be launched at water-to-air ratio of 30 to 70, 40 to 60, until 70 to 30. We will then repeat it while changing the launch angle. The launch angle is incremented at every 10 degrees, starting from 30 and ending at 60. It is important to note that the water rocket with the plasticine head weighs more than the rocket with the round head, which is the tennis head. Before launch, a person will mark the field strategically at every 10 meters. Then after launch, a person will run and measure the distance that the rocket travels. He will use a 1 meter ruler to measure the closest 10 meter marking. Now I will invite Enoch to talk about the launcher design.
Okay, as you can see on the screen, this is our launcher, but I brought the actual launcher out here to show you, but the picture may not be so clear. Okay, so I'll start from the top. Okay, this tube is where the air will travel through from the gas compressor. This part is where it is connected to a hose which is connected to the gas compressor. The air will flow in and it will come out of this tube. As you can see, over here you see some white tape. The white tape, white tape is to prevent leaks, but we wrap many layers of white tape around so that when we put the rocket in, the mouth of the rocket will fit tightly around this section, so that water will not come out. You all cannot see, but there's an O-ring around the tube which does not allow the rocket to travel, which does not allow the rocket to go down further. You can see there are some cable ties over here. The cable ties are to lock down the rocket. So when the rocket goes in, the cable ties, with the help of this reducer, the reducer will go up and lock the rocket in place. The lock is very secure and it has almost never released the rocket until it was meant to be released. Okay, so now about the launch pad. This is our launch pad, as you can see. The launch pad is basically 2 wooden boards connected by a hitch. You can see there is a wooden board over here. It is to prop up the board at a specified angle, which Imani mentioned just now, 30 degrees, 40 degrees, 50 degrees, or 60 degrees. You can see this is the top view of our rocket. There are some things over here to hold down the launcher so that the launcher can be strapped down in place and launch the rocket firmly.
We found that 2 rockets are best. So this rocket on the right, please note that this is the wrong one. This one should have angled fins instead of the straight ones you see here. So both of these were launched at 50-degree angle and 40 to 60 water to air ratio, which means that they have 40% water. And this one was the one that flew the furthest once. But this average means that we tested the average for each category, be it nose type or the fin angle, and from all the best average we came together with this rocket. So now we have to choose between this rocket and that rocket. So which one will win? We chose this one. If you know that when we launch rockets, they're affected by wind. So if we chose the one that flew the furthest ones, it's not really that accurate, as it could have been blown by the wind to go that far. But this one, however, was taken from the average of all the categories. Thus, it is more likely that this one will be consistent and fly further. Even though our project was a success, we have many areas that we could improve on. Such of them were such as how our overall launcher was much more safer, as it was only a wooden board that had sometimes nails and splinters sticking out. As me and Imani was people who were launching the rocket, we occasionally had scratches on arms and it was usually deemed unsafe. Another thing that we should improve on was how we could have enforced a warning that no one could go on the field while we were launching. Sometimes some people were still on the field playing soccer even though we have warned them several times. For further studies, we will be interested in testing out whether the viscosity of a liquid affected the performance of a water rocket. The liquid could either improve the water rocket performance or it will be worse than our original design. We have also tested on how weather affected the water rocket. Weather could affect numerous factors such as how the wind speed could increase the speed and the trajectory of where the rocket would land. For practical applications, we could have applied this for primary school students who would like to see the application of aerodynamics, such as how the theories and factors that they were taught come into play or how our water rocket launch. It will also be a great learning tool for those who will be interested in aerodynamics. It will also be used as a great environmentally friendly propulsion device that could be attached to bicycles or anything that is used on it. And thank you. Like what you see in the practical application. Because you know that cars they use a lot of energy to start moving because of something called static friction. So this guy with the rocket boosters on his skateboard, right? Imagine those rocket boosters were our rocket. So what we could do is attach rockets to the device and it will help to overcome the energy loss by static friction. Because like cars they use fuel to overcome the static friction. This one helps conserve the environment and is more eco-friendly and having carbon emissions.
So you're going to propel the user 100 kilometers per hour and in total where it's going to stop?
No, I mean just the starting part. When the car starts, it has to overcome static friction. Rocket can be used as a propulsion device.
How would you apply the design of the rocket to cars and other vehicles?
Okay, we won't be really applying the design of the rocket as Dylan mentioned, it will be used to propel cars. And I don't think cars need fins, but yeah, we won't be factoring in the design of the rocket into cars. It will just be used to start the car.
Okay, one of you mentioned viscosity just now. Who was? Who? Haris. Okay. So Haris, you were talking about viscosity. So why do you think that further research on viscosity would be important?
It would be like if you put plain water in a rocket, it will be part of our research right now. But if you put honey inside the rocket, we would not know what will happen to the rocket. That's why we're interested in finding out.
So what do you think might happen if it's more viscous than water, say honey? Will it be a better?
I have not experimented it. I will tell you if I
From what I know, the thicker and the less the liquid flows, the rocket will have a harder time to propel itself upwards at first, but you just have a harder time to propel yourself upwards at first.
But after that, it can travel further as the liquid doesn't come out so much, so the fuel lasts longer.
Okay. So Imani, I have a question for you. What were the scientific concepts that you all used in this research?
So the scientific concepts were like flight of the rocket.
Okay. It came from physics, right? So what in physics you have learned that you applied into this project? Any like concepts, theories,
Like the aerodynamics of the rocket.
aerodynamics, trajectory,
Pressure of the
pressure? You need to understand pressure. Good. The rest of the group members have anything to add on like the scientific
Like,
concepts?
for example, under physics we have like Newton's laws.
Yes.
We have trajectory. We have sometimes because the angled fins would cause the rocket to spin. We also have a bit of gyroscopes.
Okay.
Yeah.
Good. All right. Thank you.